the long math questions. I'm just going to do questions 2, 3, and 4 in this video, and then finish off 5 and 6 next time when I have some time to do it. Anyway, 2, 3, and 4 then, let's just go into it. So, okay, they've set up this Pn of x is x to the n plus x to the minus n, so therefore P1 of x is x to the 1 plus x to the minus 1. When you're sketching graphs and that you've just got a sum of two different graphs, you can actually just sketch them separately. So x to the power 1 just looks like this, obviously, it's just y equals x. Next to the minus 1 looks like this, and then you can just sort of add to them bit by bit. So like here, the sum of the two graphs is going to be the height of this graph plus the height of that graph, which is obviously very high. And here, the height of the graph is going to be this plus the other one, which is in the same place, to go up here. And then over here somewhere, it's going to be this one, which is very low, plus this one, which is very high. And you're going to end up with this kind of curved down U shape like this kind of idea and this kind of idea. This is in completely the wrong place, but that's okay. I'm going to get rid of it. And you eventually just end up with this kind of picture because it's completely the wrong place. Like I said, this point should be up here somewhere. And that's I think the lowest point. I'm not really sure. We can actually discover that though by differentiating, because of course we can differentiate that for 1 minus x to the power minus 2, and we can solve that for 0 by moving the x to the minus 2 over, and then maybe raising both sides to the power minus a half, which just gives you x or plus minus 1. And then of course this is at 1, and then you plug 1 into here to get 2, and then you put minus 1 into here to get minus 2, and you end up with your two turning points. So this is roughly what it looks like. Anyway, I think that's all I need. P2 of x show is this thing here. So P2 of x is x squared plus x to the minus 2. So, okay, what we can do is I can just take the right-hand side maybe and square P1 of x and take it away, and take 2 away from it. And if I do that and I expand those brackets, the 2's will cancel, which is P2 of x, of course, as I said here. So therefore, the right-hand side is equal to the left-hand side, and I think that's all I need to do. Find the expression for P3 of x. So what I did was I just took P1 of x and cubed it, of course, because that's how I'm going to get x cubed and x to the minus 3's. If you do that, you get this, because like the middle terms, the coefficients are obviously 1, 3, 3, 1. And then 2 of those and 1 of those makes an x in total, and 1 of those and 2 of those makes x minus 1. This is, of course, just 3 lots of P1 of x. So we end up with this here, and then rearrange it for P3 of x, and you get P1 of x cubed minus 3P1 of x. This is all quite interesting because it's going for our final 10 marks here of finding nice ways to solve these polynomials here. So take this polynomial here, and if we divide everything by x, we get to here. And if we divide everything by x again, we get to here. Now, I can do this because x equals 0 isn't a solution to this, of course, because you'd end up with 1 equals 0. But this is quite interesting because the x to the 2 and the x minus 2, well, they've given me that that's defined to be P2 of x. And x plus x minus 1 is P1 of x. So I think that's that. But then they've given me more help by telling me that, or by nudging me in the direction of showing that P2 of x is this thing here. So I can do that, which simplifies to this. And this is a quadratic written in terms of P1 of x. So it actually just factorizes to this. Apologies for those symbols there that are in the way. But it's P1 of x plus 4 into P1 of x minus 3, which means either P1 of x is minus 4 or P1 of x is 3. Which is cool because P1 of x is just x plus x to the minus 1, which is itself a quadratic once you times everything by x and move the thing over. You can solve this to get these solutions. I just used quadratic formula in my head, minus b plus minus 16 minus 4 is 12, and so on. And likewise over here, times everything by x and rearrange and use the quadratic formula, and you end up with these 4 solutions here, which is quite interesting. Just a really interesting way to solve quartic equations. Next, they take it up a step and they ask us to, okay, solve this degree 7 polynomial. Now, the key thing to start with is that this method that we used for this one isn't going to work because you can't just, because this is degree odd, you can't divide by x a few times to get all this balancing stuff happen with P2 of x and P1 of x. So first, we need to realize that because all of these coefficients are symmetric, 2, 5, 7, 7, 5, 2, 1, and because all the minuses are in just the right place, this is a dead giveaway that x equals 1 by factor theorem is just a root, because f of x is 0. Everything just immediately cancels. You do 1 plus 2 minus 5 minus 7 plus 7 plus 5 minus 2 minus 1. It all just cancels. And so x minus 1 by factor theorem is a factor. And so at this point, you can do polynomial division if you want. I just work out the terms bit by bit. So right now, for instance, I know this ends in a plus 1 because minus 1 plus 1 times plus 1 is minus 1. To get a minus 2x, I'm going to need to do, currently I've got a plus 1x from those two terms. So I need a minus 3x, I think, sorry, a plus 3x because there's already a minus there. I need a minus 3x, so it's going to be a plus 3x there to get minus 3x. And then the next term, for instance, currently I've got a plus 3x squared. I need plus 5x squared, so I'm going to need another minus 2 in here. Minus makes a plus. And I'm just going to keep going like that and work out all the terms bit by bit. It's a bit like polynomial division, but I just can't be bothered to try it out. I end up with this, and this is great because, of course, either this is 0, where x is 1, which I've already said, or this thing is 0, in which what I can do is I can just apply the ideas that we were working with earlier. If I divide everything by x to the power 3, because again, x isn't 0, so I can do that. I can then group this and this to be p3 of x. I've got 3 lots of p2 of x, and I've got minus 2 lots of p1 of x. And now I can write, because they told me to, I can write p2 of x in terms of p1 of x, and p3 of x in terms of p1 of x to get this cubic. I'll actually make the substitution y equals p1 of x at this point, just to make it easier to see. Another round of factor theorem eventually allows you to find that y equals minus 3 is a solution to this, because if you put in minus 3, these two terms cancel, and then you end up with a plus 15 minus 15, so that's going to be 0. So okay, break out the factor of y plus 3 here. You need a minus 5 here to make a minus 15 at the end, and then you notice that you've already got a minus 5y from these two. So you actually just need nothing in the middle, which means the solutions to this cubic are minus 3 and plus minus root 5. And so therefore, y was originally, of course, p1 of x. So therefore, p1 of x is either minus 3 or plus minus root 5. And then you just have 3 quadratic equations to solve. Either this one, because that's p1 of x, remember, or this one, times everything by x and rearrange, times everything by x and rearrange, times everything by x and rearrange. Use quadratic formula a bunch of times, and we end up with these 3, or I should say 6 solutions, along with the 7th solution that we found via our original bout of factor theorem. Quite a nice little question there, and I think that's question 2 done. Question 3 then is also quite interesting. I'm not allowed to differentiate or use calculus for any of this, that's fine. Without differentiating, find the maximum value of this. Well, 2x plus 30 as a graph transformation just shifts the graph left and right and squashes it horizontally. So the maximum value doesn't change, it's still 1, right? The max value of cos is just 1, and it hasn't been transformed vertically in any way. So the max value is still just 1. Now find the max value of this. Let's make a substitution for u equals cos 2x plus 30. And this turns out to be u into 1 minus u, which expands to u minus u squared. This is just a quadratic. I can complete the square. I think I could probably get away with differentiating this, but maybe this suggests I'm not allowed to differentiate at any point. So I'm going to complete the square on this instead, which gives me this. It's a bit awkward with the minus here, but it just about works out. And now I'm just thinking about the maximum value of this. Well, of course, that happens when this thing is 0 and I just get a quarter out. Now, the only thing is, can this thing actually be 0? That would imply that u needs to be a half to make this cancel out. But cos of something could be a half, right? Again, if it's just been shifted horizontally. So that's fine. So I think the maximum value is just going to be this half over here. Hence, write down the maximum value of this. So I think this is very similar. I'm going to, I think I did something similar in the multiple choice questions. I'm going to put this 5 and this 5 on its own outside and then make the same substitution. And I end up with this. Of course, I already know the maximum value of this object here is a quarter. So then I just need to do a quarter to the power 5 because it's the same function as this one was, of course. You get this if you want to write it out properly. But you get the maximum is a quarter to the power 5. A quarter is 1 half squared. So that's 1 half to the power 10, which is 1 over 1024, just because I know 2 to the power 10 is 1024. Final bit is the maximum value of this. Now, there's quite a few things going on here. Most critically is this 150 minus 3x as compared to 3x minus 60. Now, if I'm going to have any chance of doing this question, the arguments of this cos here is going to have to match. So how do I do that? Well, the first thing I thought was cos is an even function. So I can actually just swap the 3x minus 150 over because if the input is negative, the original one, it doesn't make a difference to cos because it's symmetrical around the y-axis. So that was the first thing I did. But that doesn't actually really help. We've still got a difference of 90 degrees between 3x minus 60 and 3x minus 50. So that doesn't quite work until I realized that actually there is another identity that you're supposed to know in year 12. And we're thinking year 12 identities here because that's the only thing you're supposed to know in math, which is this other identity of sine of x is equal to cos of x minus 90. So we have a difference of 90 degrees in the input, switches from cos to sine. And that triggered this idea over here. Where does 1 minus cos squared come in a lot? Well, 1 minus cos squared is sine squared. So I think actually the way to do this is to swap these into sines, which is not obvious at all, but we can use a combination of 1 minus cos squared is sine squared to make this one into a sine. And we can make this one into a sine using this idea, because if we've got that this is actually 3x minus 150, we can write 3x minus 150 as 3x minus 60 minus 90, right? And then we can just say, well, okay, there's the input, 3x minus 60 minus 90. Therefore, this thing here must be sine of 3x minus 60, based on this identity above, where x is being replaced with 3x minus 60. So this thing here, which is this thing here, which is this thing here, can be replaced with sine of 3x minus 60, and we end up with this thing here. 1 minus cos squared is, of course, sine squared. And now the inputs are the same. It's in terms of sine, but that seems okay. Of course, sine squared, I think I made a substitution here. Yeah, u equals sine of that. Cool. So now we can make this u squared to the 4 is just u to the 8. And now I can bring that 8 to the top to make this idea here. Expand that out if you want to. Something to the power 8. Now, a negative to the power 8 is the same as a positive to the power 8. So I just swapped those two terms around because I'm allowed to do that. That just made it easier for me to complete the square, which is, of course, what I intend to do here. And now this is a bit more complicated than the first couple of questions because we can't make this thing 0 because u can't be 1.5, which is what it would need to make this 0. It can't be 1.5, of course, because sine is maximum at 1. Again, this is just a horizontal shift around, right? So we can't do that. But what we can do is just make u as small as possible, i.e. minus 1. Because if we do that, minus 1 minus 3 over 2 is minus 5 over 2. Squared is 25 over 4, minus 9 over 4 is 16 over 4, which is 4, and which makes that 4 to the power 8. And it's possible that that's the maximum value. I do also want to try what happens if u is equal to 1, just because I don't know which is the max yet. So if u equals 1, 1 minus 3 over 2 is minus a half, squared is a quarter, 1 quarter minus 9 over 4 is 8 over 4, which is 2, and 2 to the power 8 is less than 4 to the power 8. So I'm pretty happy that 4 to the power 8 is the maximum value here, and I'll say that's my final answer. Question 4 then is a different sort of question here. We've got parabola y equals a half x squared. So okay, let's just draw that. Point obviously a half a squared. I'll just say that's there somewhere. A bigger than 0, fine. The line L is normal to the parabola a, so that's going this way, of course, at 90 degrees. And b lies on this line L, such that we've got a distance of d from a, up and to the left, so over here somewhere. So like it could be there, for instance, with that distance being d from point to point. Okay, so that's the setup. Find the coordinates of b in terms of a and d. Okay, a few things to do here. First, I differentiated a half x squared to just get x, and I put in the value of a to find the gradient of the parabola. The gradient of the parabola is just a at a, which means the gradient of the line is minus 1 over a, because of course it's the negative reciprocal, because it's normal, it's 90 degrees. Okay, so this gradient is minus 1 over a, which means we could make a little triangle of a across and 1 up in this direction, which means this distance across in this little triangle would be root 1 plus a squared by Pythagoras. But of course, I've got a distance of d from point to point. So if I just connect a little triangle there, I must have two similar triangles here because, of course, they're following the same gradient of this line here. And so therefore, the scale factor from this triangle to this triangle, I think, is just d over root 1 plus a squared. So this length here is just a times d over root 1 plus a squared. And this one is just 1 times d over this, which is d over that. And now I think I'm pretty much done. The coordinate of b is going to be a minus this horizontal journey here to get to this x coordinate. So a minus this. And the y coordinate will be this plus this because we're going upwards. And we'll end up with this, I think, here as our coordinates of b. Show in order for b to lie on the parabola, we must have this thing here. So for b to be on the parabola, the x and the y coordinate have got to follow this rule here. So I'm going to say that this thing here, which is the y coordinate, can go in there, and this thing here, which is the x coordinate, can go in there, and I'll end up with this equation, which must be satisfied. I can double everything, and I can also expand this out. It's double brackets, remember, so it's a times a, which is a squared, into two cross terms, which is minus 2 lots of a times this, which is this, and then this thing squared is just this here at the end with a plus. The a squareds cancel. When I add this to both sides, because the same denominator is here, I just get 2d plus 2a squared d. Now, d isn't 0, and I think the justification for d not being 0, definitely not being 0, is that b lies above and to the left of a, whereas if d was 0, b would lie on a. So I think this line here implies that d isn't 0. So that's fine. That means I can divide everything by d, and I'll be okay. I'm going to times everything by 1 plus a squared here, which will cancel a little bit with this root 1 plus a squared to leave me a root 1 plus a squared on top, and get rid of this obviously on bottom. Factorize out 2 from this, and of course this is 1 plus a squared to the power 1, this is 1 plus a squared to the power of a half, 1 plus a half is 3 over 2, and I think I end up with exactly what they wanted me to get as the star just here. Next, let t equal a squared. Well, that's quite easy. That means we've got td equals 2 into 1 plus t to the 3 over 2. And express the equality in the form d to the power 2/3. So divide everything by t, and then raise both sides to the power 2/3 to get this. This 2/3 needs to distribute down to the 2, down to this bracket here, and 2/3 cancels with 3 over 2, of course, because they times together to make 1. And then it also needs to distribute down to that t there. Of course, I can expand that out if I want to, and then I can divide terms individually by t to the 2/3, which will give me 2 to the power 2/3 times t to the minus 2/3, plus 2 to the power 2/3, and then this is a t to the 1, divide by t to the 2/3 is t to the 1/3. I end up with this here, which, so I'll just define that to be f of t. Find the minimum value of f of t. So I think I can differentiate this using year 12 maths, that's what I'll do. Minus 2/3 jumps down to the front here, and then take 1 away from this to get minus 5/3. A third down to the front to make it minus 2/3. Minimum value means I want to solve that for 0. I'm going to times everything here by 3, and also divide everything by 2 to the power 2/3, and I think I just get this because the 0 is obviously unaffected. And now I think I can times everything by t to the power 2/3, I think, because if I times everything by t to the power positive 2/3, it will cancel with this to make a 1, and add 2/3 this and get minus 3/3, which is just minus 1. So I think I get this. Move this over, divide by 2. This is obviously 1 over t, which means t just needs to be 2. And then the minimum value of f of t, if it happens when t is 2, put t as 2 into here. And very nice stuff happens here. This cancels down to 1, and this adds these two things together to get 2 to the 1, which is 2. So it's just 1 plus 2, which is 3. And that's hopefully the minimum value of f of t. I thought probably I just needed to prove that very quickly, although I'm not sure that I do. I wasn't really thinking it through, maybe, I'm not sure. But I just decided to put in t as 1 into this, because that seemed like a really easy thing to do, because I just want to show that this isn't a maximum. I just wanted to prove that I haven't found a maximum by mistake. Maybe there's some other way to logically show it. You could, of course, differentiate again, but I thought that would be too much work. So I just put in f of 1, because 1 to the power anything is still 1, so that made it really easy. You just end up with 2 lots of 2 to the power 2/3, which is 2 to the 1 times this, which is 2 to the 5/3. Now, which is bigger, 3 or 2 to the 5/3? Well, if you cube both, this one turns into a 27, and this one turns into a 2 to the 5, which is 32. So this one cubes to something bigger, which means it's bigger, which means that f of 1 is bigger than f of 2, which means f of 2 can't be a maximum, and therefore I think I can say that's definitely a minimum. I don't know whether I need to do any of that, but whatever. Hence show that star holds for some real value a if and only d is greater than some equal value. So okay, we've just shown that the minimum value of f of this f of t here is 3, which means going back to this, the f of t was equal to d to the power 2/3, remember? And the minimum this can be is 3. So therefore, the minimum d can be is 2d to the power 2/3 would be equal to 3 to make d minimum. Raise both sides to the power 3 over 2, and we get d as a minimum that d can be is this, and therefore if d is greater or equal to this, then we'll be okay. And this, I guess, is the root of 3 cubed, which is root 3 times root 3 times root 3, is 3 root 3, I guess, but I couldn't be bothered to write that. Anyway, I'll see you for parts 5 and 6 in a second.